What is the main problem that Chameleon aims to solve in multimodal foundation models?
Chameleon aims to solve the main problem in multimodal foundation models by addressing the limitation of modeling different modalities separately, which can hinder the integration of information across modalities and the generation of multimodal documents with arbitrary sequences of images and text. Chameleon presents a family of mixed-modal models designed for generating and reasoning with mixed sequences of interleaved textual and image content from the start, using a uniform architecture trained end-to-end on a mixture of all modalities. This early fusion approach allows for seamless reasoning and generation across modalities, enabling the model to handle tasks such as image generation, understanding, and reasoning over images, as well as text-only tasks. By using fully token-based representations for both image and text modalities, Chameleon overcomes the need for separate encoders or decoders for each modality, allowing for a more flexible and efficient multimodal modeling approach.
How does the Chameleon model work in integrating information across different modalities, such as images and text? Illustrate step by step.
The Chameleon model integrates information across different modalities, such as images and text, through an early fusion token-based approach. Firstly, Chameleon represents images as discrete tokens, similar to words in text, using a new image tokenizer that encodes images into tokens from a codebook. This allows for a uniform representation of both image and text modalities. Secondly, during pre-training, Chameleon trains on a mixture of text-only text-image pairs and interleaved text-image documents, allowing it to learn to generate and reason over mixed sequences of image and text tokens. Thirdly, Chameleon uses a shared representational space from the start, projecting all modalities into this space, enabling seamless reasoning and generation across modalities without the need for separate encoders or decoders. Additionally, Chameleon employs architectural innovations like query key normalization and revised layer norms in the transformer architecture to ensure stable training in the mixed-modal setting. These modifications are crucial for optimization stability and scaling in a model that processes multiple modalities simultaneously. Overall, Chameleon's design enables it to reason over and generate interleaved image-text sequences effectively, setting a new standard for multimodal foundation models by allowing for flexible integration of information across different modalities.
What are the theoretical or practical benefits of using the early fusion token-based approach in Chameleon compared to late fusion models like Flamingo or IDEFICS?
The theoretical and practical benefits of using the early fusion token-based approach in Chameleon compared to late fusion models like Flamingo or IDEFICS lie in the seamless integration of multiple modalities without the need for separate encoders or decoders. Chameleon's early fusion approach allows for joint reasoning and generation across interleaved image and text sequences within a unified architecture. This results in more efficient information integration and processing, enabling Chameleon to flexibly reason over and generate mixed-modal content without the complexity of modality-specific components. Additionally, the early fusion token-based approach in Chameleon simplifies the model architecture, leading to improved optimization stability and scalability, as discussed in the paper. By projecting all modalities into a shared representational space from the start, Chameleon can achieve better alignment and performance on mixed-modal tasks, as demonstrated in the extensive evaluations presented in the paper. Overall, the early fusion token-based approach in Chameleon offers a more streamlined and effective way to handle multimodal tasks compared to late fusion models, enhancing the model's capabilities in reasoning and generating mixed sequences of images and text.
How is the stability of training in the mixed-modal setting addressed in the Chameleon model, particularly in terms of optimization stability and scaling?
The stability of training in the mixed-modal setting in the Chameleon model is addressed through a combination of architectural innovations and training techniques. To ensure optimization stability and scaling, Chameleon introduces novel modifications to the transformer architecture, such as query key normalization and revised placement of layer norms. These modifications are crucial for stable training in the mixed-modal setting. Additionally, Chameleon adapts supervised fine-tuning approaches used for text-only large language models to the mixed-modal setting, enabling strong alignment at scale. The model uses an early fusion approach where all modalities are projected into a shared representational space from the start, allowing for seamless reasoning and generation across modalities. Furthermore, Chameleon employs a recipe for architecture and optimization that includes using the AtomW optimizer, a linear warm-up of 4,000 steps, exponential decay schedule of the learning rate, weight decay, and global gradient clipping. The model also applies Z-loss regularization during training to stabilize the training process. These strategies help Chameleon achieve stability and scalability in training, even at larger scales such as Chameleon 34B, which is trained on 5x the number of tokens as LLAMA2.
What results were achieved by Chameleon on visual question answering and image captioning benchmarks compared to models like Flamingo, IDEFICS, and LLAVA 1.5?
Chameleon achieved state-of-the-art performance on visual question answering and image captioning benchmarks. Specifically, Chameleon 34B outperformed models like Flamingo, IDEFICS, and LLAVA 1.5 on visual question answering tasks, matching the performance of larger models like Flamingo and IDEFICS with fewer shots. In image captioning evaluations, Chameleon 34B surpassed the larger 80B models of Flamingo and IDEFICS on the MS COCO dataset with 32 shots, while matching their performance on the Flickr 30K dataset. Additionally, in fine-tuned, closed-source models, both the multitask and supervised fine-tuning variants of Chameleon 34B outperformed all other models on the MS COCO dataset. For the Flickr 30K dataset, the supervised fine-tuned model of Chameleon 34B outperformed other models, with the multitask model being a close competitor. Overall, Chameleon demonstrated competitive performance on both visual question answering and image captioning tasks, showcasing its effectiveness in generating mixed-modal responses with fewer training examples and smaller model sizes compared to existing models.
What are the limitations or drawbacks of the Chameleon model, especially in tasks like heavy OCR-related image reconstruction tasks?
The limitations or drawbacks of the Chameleon model, especially in tasks like heavy OCR-related image reconstruction tasks, include the core weakness of the image tokenizer in reconstructing images with a large amount of text, which can upper bound the capability of the models for heavy OCR-related tasks. This limitation arises from the tokenizer's difficulty in handling images with extensive text content, impacting the model's performance in tasks requiring accurate reconstruction of such images. Additionally, the early fusion approach of Chameleon, where all modalities are projected into a shared representational space from the start, may present challenges in optimizing the model for tasks that heavily rely on detailed image-text interactions, such as OCR-related tasks. Furthermore, the model's reliance on token-based representations for both images and text may limit its ability to capture fine-grained details in images with complex textual content, affecting its performance in tasks requiring precise image-text alignment and reconstruction. Overall, while Chameleon excels in mixed-modal reasoning and generation tasks, its limitations in handling heavy OCR-related image reconstruction tasks highlight areas where further improvements or specialized architectures may be needed for optimal performance in such specific tasks.